All right, well, welcome for the last subtopic on motor skills, which is descriptive models of response time. So 10.4, 10.5 talked about predictive models of reaction and movement time, which add up to response time. These are descriptive models. So predictive, more mathematical, and descriptive, more real world. Okay, so a big difference here is, the Hickheim and Fitz's law. These are idealized sorts of calculations. They are a good idea to go through the exercise to determine kind of boundary conditions for, here's a maximum and minimum for what we might expect. But the real world is messier, right? And so, when you start combining all the complexities of let's be in a real car on a real road with real lighting conditions, et cetera, all of these factors come into play. So sometimes it becomes, more useful to get empirical data, collect data with a stopwatch, and really get so much data in so many different circumstances that you can describe basically the factors at play and how they influence humans, but in a way that isn't as mathematical. It's not as modeled like Hickheim and Fitz's law. So yeah, things are, signal discriminability. Can I tell if that's a skunk or it's a tire in the road? Am I doing this repetitively? That's going to affect how I respond. Practice, for example. All right, so all of these are reasons why these predictive models, they're limited. Like they're good for realizing this is an idealized context or saying here's kind of the minimum and maximum we might expect, but get the stopwatch out if you want to get results that are very translatable to the real world, basically. So this is one example, what we call the chaining model, and it's basically a table-based approach. So McGee, 1989, it's an older one now, collected a ton of data about how long does it take people to see there's something in the roadway and decide what to do about it and act on it and, depress a brake. And so they call this the chaining model because in this case, you would look at the aspects of what a human is doing in a certain context, and you chain together basically the time components for this process, right? So for example, if there is an aspect of perception, I need to see and perceive that that's a skunk in the roadway before I know what to do about it. Then I have to factor in all of these, time factors. If I have to make a decision about what to do, simple RT or choice RT, we're going to add some time. But the amount of time in this case, you can see this isn't about how many choices am I considering, like log base 2 of, the number of choices, whatever. This is a very generic stopwatch based number, that comes here. So this is not saying, well, how many things am I deciding about? It's a blanket. If there is a decision, we're going to approximate what that means to a human by adding this much time. All right, so for all of these, I like 85th percentile. I do want to point out that this is a kind of a rule of thumb standard for transportation engineering. What this means, we're going to go into more detail about 85th percentile, what that means in the next topic, anthropometry. But for now, just this is 85% of the driving public will be able to achieve this or faster. That's the way you can interpret that. And that is the design standard. So this is where the transportation engineers would say, this is the standard for which we're designing our speed limits, on this road, for example. All right, so let's go back to our skunk example, poor skunk. How long until 85% of drivers, from the point where they have the chance to see this item in the roadway, which is a skunk, until their foot is on the brake and they are beginning to depress it. So we'll use that 85th percentile column, and I just reproduced it here. So assuming we're not expecting any skunk, we're just cresting a hill and looking down and, oh, there's something there. So no expectation means I need to add latency. I need to add time for my eyes to focus on this new item and process what it is, fixate on it, and recognize. So I'm adding all of these, 0.31, I'm adding all of those components here. So far, 1.1 seconds after the first beam of light from the skunk reached my retina, 1.1 seconds later, if I'm designing for the 85th percentile, they have a realization, hey, that's a skunk. Now, what do I decide about it? I'm going to say I'm going to break, but whatever. Again, this is the empirically derived approximation. This does not take into account how many different possible outcomes there are, like Hick-Hyman does, right? Hick-Hyman definitely matters how many different options and what are their probabilities, right? In this case, these descriptive models will just say, is there a decision on the roadway, yay or nay? And if so, we're going to add 0.85 seconds to it. Decide what you're going to do about the fact that you now realize that's a skunk. So we're almost 2 seconds in already, 1.95. And then fundamentally, I'm going to add 1.24 seconds. That is the 85th percentile. Where am I going to get 1.24 seconds from when the light beam strikes my eye? So yes, 3.19 seconds is going to be within the 85th percentile of humans, the worst case. And by we say worst case, this doesn't mean like varying on people. This varies on the context. And so the worst case is I have no knowledge of a skunk. I crest the hill, boom. This is, I view it and I wasn't prepared at all. And I have to take all of these time costs into account. Now, worst case, 3.19 seconds. That's probably where you want to set your design standard. This should dictate what our speed limit is. So if you can say it's going to take 3.19 seconds for the amount of time from I see that's a skunk to I am able to put my foot on the brake. Now, if we want to factor in, well, how long is it going to take you to stop once foot's on the brake? You can factor in how long until, how far away can I see that that's a skunk? Therefore, you have your distance. Now you can set, your traveling speed, your speed limit, based on how quickly we expect humans to be able to respond. All right, so worst case, that's a good one for your design standard. But if you're curious, well, how do we get this best case? Let's just say the best case example here, D, right? So here's how that might happen. So first of all, I'll go to the 50th percentile. Let's go to our graph and find the fastest overall. And what that means again is 50% of people will be this good or faster. And so it's a lower speed or faster amount of time, smaller amount of time than the 85th percentile, because that allows 85% of people to be at it or less. All right, so anyway, let's say, we're best case here. I'm cresting a hill and somebody told me, hey, I heard there's a skunk on the ground up ahead. Look out for it. So I'm cresting the hill. I'm expecting something. I'm looking at the ground already. I crest the hill. Boom. I lock onto it. I don't have the latency because I did expect it, or I have very minimal latency. I don't have the eye movement because I've already been focusing at the roadway. And so really, I just have fixation and recognition to process here. I may know that, hey, you already told me there's a skunk. As soon as I see the skunk, I'm going to brake. Maybe I've already pre-decided that, right? So I don't have to factor that in here. And let's just say, okay, so now I've got 0.2 plus 0.4 plus, it is still going to take me that long to get on the brake. So I add those up, and 1.45 seconds is my best case scenario. And that's how we calculated that. All right, so that's it for topic 10. I hope you enjoyed all the motor moving. All right, thanks everybody.